Early in my career, every time I picked a database, I asked the same question. Should I use SQL or NoSQL? I'd Google it, read a few threads, and just pick one. Looking back, that was the wrong question entirely. The most expensive database mistake isn't picking SQL over NoSQL. It's choosing a data model that doesn't match your workload, and it gets more painful the bigger you scale. Today, let's learn to reason about database selection like a senior engineer. Not which is better, but how to weigh the trade-offs. Let's start with SQL. Relational databases like Postgres and MySQL weren't designed badly. They were built for a specific world. They optimized 5 things: strong ACID guarantees, referential integrity, complex relational queries with joins, safe concurrency control, and deterministic consistency. But that was an era of single-region apps, where partitions were rare and scaling up. A bigger server beat scaling out. Millions of global users weren't a thing. They optimized for correctness first. Distribution was an afterthought. That distinction matters for what happened next. Then Facebook, Google, and Amazon happened, and the constraints completely changed. Now, multi-region users expecting fast responses everywhere. Millions of writes per second. Always-on uptime. Network partitions as normal events. And datasets bigger than any single machine, petabytes. The challenge was no longer just store data safely. It became store massive data globally, tolerate failure, and stay fast all at once. Here's the key insight. This is a distributed systems problem, not a database problem. SQL didn't get worse. The problem shifted underneath it. When vertical scaling hits its ceiling, relational databases scale out through sharding, splitting data across independent instances, each holding a slice. You can shard by range, like user ID ranges, by hashing the key or with a directory lookup. Sounds clean, but here's where it gets painful. Cross-shard joins get expensive, pulling from multiple databases and merging in memory. And a transaction across 2 shards is genuinely hard to coordinate. Resharding is risky, rebalancing live without dropping a write. Hot partitions overload one shard while others sit idle, plus the overhead of running many clusters. The punchline: your sharded SQL database has become a distributed system, but one you built yourself bolt by bolt, without the purpose-built guarantees. Which brings back the one constraint that governs all of this: the cap theorem. You can't have consistency, availability, and partition tolerance all at once. Partitions are non-negotiable, so the real choice is CP, or a PCP stays consistent and may reject requests, like Google Spanner. A P stays available but allows temporary inconsistency, like Cassandra. Every distributed database picks a spot on that spectrum. When you choose one, you're choosing your trade-off. There's a full cap video if you want the deep dive. Now, NoSQL isn't one thing. It's a family of models, each built for a workload. Let's walk through 4. Document stores like MongoDB keep data as flexible JSON-like documents. Great for catalogs and profiles where the schema changes often. You trade strict integrity for agility. Key-value stores like Redis and DynamoDB are the simplest. Give a key, get a value. Perfect for caching, sessions, and leaderboards, but you can only query by key. Wide-column stores like Cassandra and HBase give each row its own columns, built for time series and write-heavy global scale. Huge write throughput, but you design around your queries up front. And graph databases like Neo4j model nodes and relationships, built to traverse connections, social graphs, recommendations, fraud detection, phenomenal at relationships, wrong for everything else. Here's the biggest mindset shift. No serious system at scale uses a single database. A realistic architecture, Postgres for financial transactions, Redis for caching and sessions, Cassandra for activity feeds, Elasticsearch for full-text search, and S3 for file storage. Each database solves the workload it was built for. That's not complexity for its own sake. It's architectural maturity, the right tool for each job. The cost is operational. More clusters, more monitoring, more on-call. For startups, one database is often right. At scale, this polyglot approach is the norm. So when you pick a database, here's the framework a senior engineer actually uses. 1. What's the access pattern? By key, range, search, or relationship. That drives your model most. 2. The read-write ratio. Read-heavy suits relational with replicas. Write-heavy at scale needs Cassandra or DynamoDB3. Consistency. Can users see slightly stale data, or is this financial? 4. What failures must you survive, single or multi-region? 5. How will you scale 10x or 1000x? 6. What operational complexity can you afford? The key insight. Database selection isn't about popularity. It's about workload alignment. So the mental model. Start with the right question. What are my access patterns, scale, and consistency needs? Not SQL or NoSQL. Every database is a bundle of trade-offs. Relational trades distribution for correctness. Wide column trades query flexibility for write throughput. Key value trades richness for speed. And at production scale, the answer is almost never one database. It's the right database for each workload. If this clicked, check out my ACID and CAP videos, the foundation under all of this. And tell me which model to go deep on next.